Hallo, liebes Publikum. Da es jetzt sehr voll werden wird, darf ich euch jetzt schon bitten, wenn möglich, nach innen in die Reihen einzurutschen, damit außen noch Plätze frei bleiben oder genutzt werden können. Danke. Okay, hello. It's getting full, so it's defragmentation time. I think, or I hope everybody knows this game, so please, if there are free seats, raise hand, and if there are free seats in the middle, please move to the middle so that the free places are on the outside. Thank you.
Apparently, so.
Yep. I think you can. Yep.
I hope not.
Oh, look.
That's weird. Never mind.
Ja, wahrscheinlich. Also, wenn er nach einer Zeit ist. Wir wissen nicht ganz genau, wie lange wir sprechen werden. Aber wenn er nach einer Zeit ist, hier wird es alles dann frei, wenn wir das machen. Sind ja noch
3 minutes.
Ja, das ist auch. Nee, das erste Mal. Das erste Mal? Wir alle. This will be a great talk. Later you can look at the performance of the screen.
So what does this screen show? Does this show the same thing as this?
Shows your screen.
Okay.
Okay, great.
It's a reference.
Okay.
Okay, so you don't have to look always on that. You can look.
Right. Okay. Yeah. Cool.
So you. Okay.
Okay.
We start.
Cursor.
Okay, hello, good evening. We have some people coming here, so if there are free seats, I would again ask, raise hands.
Oh, it works.
There are lots of free seats in the
What? Yeah. No, it works.
front left of the hall.
So it's like Pluto, Derek, Pluto.
People joining now, please get seated so that we can start. Thank you. Okay. Ich sag's diesmal auf Deutsch, weil mein großartiger Stage Manager Chester mich zu Recht darauf hingewiesen hat. Es gibt eine Übersetzung und die ist auf Deck 8040, 8040. Der Talk ist in English. Okay. One thing I need your attention before we can start, and that is, I would ask you really for some things. One thing is, try, if you want to leave in the talk, which I hope you won't do, please try to hit as few Mate bottles as ever possible. Thank you. This is one thing. But much better is just stay. Don't leave 3 minutes, and when we have the Q&A in the end, if we come to the Q&A, please consider just staying. And if you really have to leave, please do so, but silent. Thank you.
Are we starting?
Okay, welcome to our last talk in this hall today. It's about console hacking, and I guess that's the reason why you are here. Console hacking has a long tradition at our great conference, and we have seen lots of funny things, people doing stuff with Xboxes, PlayStations, and everything. Okay, today we got a team which deals with the Nintendo DS, so give a warm applause for Pluto, Derek, and Smea.
Hi, I'm Smea. This is Pluto. This is Derek. And today we're going to talk to you about our work on the Nintendo 3DS. So the way this talk is going to be structured is we're just going to go over all the hardware, organization, software, like just give you a basic overview of how the system works. And after that, we're going to go into basically every layer of security the system has and break every one of them. Okay, so as you probably know, the original Nintendo 3DS was released in 2011. It's a system that's kind of underpowered. It's got an ARM11 dual-core CPU. 268 megahertz. It's got a nice proprietary GPU, a bit of RAM, you know, the usual. It's also backwards compatible with DS games, which is nice. Then the new 3DS was released in 2014 and 2015. There's like different regions, and it's basically just the same console, just some improvements in the hardware. You've got a better CPU. It's got more cores. It's faster. It's got more RAM. Basically everywhere, so it's just the same thing. It runs the same software exactly. It's got some exclusive software, but not much. So in terms of a hardware overview, this is what we're going to talk about looks like, general. So you've got the top part right here, which is what we're going to go into first. This is like the ARM11 part. Basically, you've got the ARM11, which is the main CPU. It runs the main operating system. It has 2 cores, as I just said, or 4 cores. And so it runs the main operating system, it runs the games, it runs all the applications. Basically, it's just, if you're doing something on your 3DS that you can see it happening, it's happening on that CPU. It's got access to all of main memory, so that includes FCRAM, which is 128 megabytes or 256 megabytes, depending on which model it is. And FCRAM is actually divided into 3 separate regions. So you first got the application region, which contains the currently running game or application. The system region, which contains applets, which are basically tiny applications which run in the background. So that includes the home menu, which is actually always running in the background, and the web browser, which you can actually run at the same time as your game, so it has to run there. And then you've got the base region, which is more interesting. It contains all the system modules of the operating system, as well as some kernel data, such as handle tables and MMU tables, so it's kind of sensitive stuff. And then you've got WRAM, which is tiny and contains all of the kernel code and, well, most of the kernel structures as well. So it's also an interesting target. Then we've got the lower part, which is the ARM9 part of the hardware. So the ARM9 is basically a separate, well, it's an entirely separate CPU, which has access to, well, so it runs basically the same microkernel as the ARM11. It's mostly the same code. It's just got some fewer features. Mostly it runs a single process, which is called Process 9, which does everything the ARM9 does. Beyond that, the role of the ARM9 is to broker access to hardware that might be, well, sensitive in terms of security. So one of the things it does is it brokers access to all storage media. So that includes the permanent storage as well as the SD card. And then it does all sorts of crypto stuff, which is really important. And it does that by using hardware, actually. So there's this hardware key scrambler, which is used to store secrets in hardware, basically. The idea is you feed it 2 separate keys, and it's going to generate a normal key and feed that directly into the hardware implementation of the AES algorithm. So that way, we never actually see the final keys. So that's something that's kind of annoying. And then beyond that, what you can see is the ARM9 has access to all of main memory without much of, well, without any restrictions. But it's also got its own internal memory, which the ARM11 does not have access to. So the ARM9 internal memory is where the ARM9 stores all of its code, all of its data. And this way, we can't actually take over the ARM9 just from the ARM11 without some kind of exploit. So it's basically a security CPU. So this leads us to having 4 layers of security. Basically, you're first going to have the ARM11 user land, which is what, well, like your games, your applications, whatever. On top of that, you're going to have, well, below that, I guess, the ARM11 kernel. So that's going to have full privileges on the ARM11. And then you're going to have ARM9 user land, which is process 9. And beyond that, you have ARM9 kernel mode. So that's in theory. In practice, the microkernel has a system call, which we call syscall. We call it SVC backdoor, because essentially you feed it a function pointer and it just executes that function in kernel mode. So you don't even need an exploit if you have access to that syscall. Of course, on the ARM11, no application or title or anything ever has access to that. But on the ARM9, Process 9 actually has access to it. Which means that from here, we actually, well, user land in kernel mode are not, well, basically the same thing. If you got user land on the ARM9, you got kernel mode. So that's nice. Beyond that, in terms of cryptography on the system, basically they went all out. So anything that can be signed is signed. So that includes the firmware, that includes every application. Signatures are checked not only at install time, but also at runtime. So that's something to keep in mind. Same thing, anything that can be encrypted is encrypted. And anything that can be made, well, console specific through cryptography or authentication, such as the internal permanent storage or the data that's stored on the SD card or save games or extra data for games. This is all made console specific and game card specific in terms of in regards to save games. So that's kind of annoying as well. And of course, all this is handled by the ARM9 using the hardware, the crypto hardware. So we got to get through that if we want to do interesting things. So first, we're going to go through the first layer, which is ARM11 userland, the ARM11 userland, basically getting a foothold into the system. So we first need to find some kind of entry point. There are problems, well, there are challenges there. One of the challenges is that the system implements strict data execution prevention. So existing pages will never be will never be read-write executable. It's only going to be read-only or read-writable or read-executable. There's no way from a standard application to reprotect or map new pages that are read-write executable because all the system calls are locked out except for higher privilege system modules. Another thing is that there's no ASLR, so that's not a challenge, that's actually kind of nice. The nice thing here is that that makes save game vulnerabilities totally fair game because, well, we don't need an actual scripting environment or any kind of exotic vulnerability to exploit this, as long as we can get past depth somehow. And then, of course, the fact that all save games are both encrypted and made specific either to the game card or the game console in the case of eShop games is really annoying for save game vulnerabilities because basically you can't use those as an initial entry point in most cases because, well, you can't generate the right, right ASMAC or just you don't know the right cryptography. So that's annoying. Thankfully, the 3DS runs WebKit in, so that's nice. You can always use that. So WebKit is used in a number of places. Obviously, it's used in the main web browser, which you can access from home menu. It's also used in the YouTube application, which is available free on the eShop and doesn't use any kind of authentication, client-side authentication for the server, so you can just redirect traffic through like a DNS server, for example. Miiverse applet, other stuff also uses it. Slightly more secure, but might be usable at some point. I don't know. Anywho, the important part here is that it's not only using WebKit, it's using a very old version of WebKit. Basically, they do cherry pick some patches into the version of WebKit they use, but only after we exploit those vulnerabilities. So it comes a little too late most of the time. So yeah, this has been used by multiple people, most notably Yellow's8, but it's proven to be a very efficient, reliable entry point. Beyond that, we've got Cubic Ninja as an initial entry point. Cubic Ninja is a game that was released in 2011 on the Nintendo 3DS. And it's nice because it actually allows users to share levels that they make themselves through QR codes. And also, it is really bad at parsing those levels. So what you can do is just, well, manufacture your own QR code that's going to crash the game and give you access. So these are nice initial entry points. So once we've got this, what you have to remember is that we might be able to crash the game, might be able to control registers, but we don't actually have our own code running because of DEP. So the obvious solution to hit this is to use ROP. For those of you who are not familiar with ROP, it's just you build your own fake stack that lets you return into code snippets that are located right before return instructions. That way, so this is an example, you can just jump to this kind of instruction, so pop R0 PC, and then this is going to let you load your own register value, and then it's going to jump to the next instruction that you give it. So this is a way of executing code without actually executing code, which is widely used, so this is like the obvious thing to do. Of course, ROP is annoying. It's very limiting. It can be enough to actually execute an exploit to get higher privileges, but well, overall, it's just annoying and very limiting for Homebrew, for example. And of course, as I mentioned earlier, we don't have access to any of the system calls that would let us map read-writable, executable pages. As also, the system does support dynamically linked libraries, so that might be a way, but these are signed and checked in places that we can't access at this point. So what we're going to look at next is the GPU to see if we can use that to bypass DEP. What you can see here is that the GPU has access not only to video RAM, but also to FCRAM, which is, if you'll recall, the main memory. So if we look at this with all the different memory regions, we've got the application region here, which is entirely contained within what the GPU can access within FCRAM. Because the GPU cannot actually access all of the FCRAM, so that's kind of limiting. But what you can see here is that, of course, application code is within range of the GPU's level of access. The reason the GPU has to access FCRAM and video RAM through DMA, by the way, is so that it can access information such as textures, vertex, buffers, this sort of thing. So it's actually kind of important. And the reason it can write to it is because it has to render its data somewhere. The point is that we can use this to render data into main memory. And main memory contains application code. And since the physical layout is actually completely deterministic, and even if it wasn't, we could just use the read capabilities of the GPU to search for what we're looking for. Well, we can use this to overwrite our current application's text section, and we get code execution that way in spite of DEP. Yeah, so this way we get code execution. We execute our own on-site code, which is great. It's great, but we are still confined within the application sandbox. So we bypass DEP. We're inside the sandbox. What this means is that we can only access our current application's safe data. So if we want to install some kind of secondary exploit, this is too limiting. We can only access certain services as system calls, which is also limiting and frustrating. And we can't alter the memory layout, so we can't allocate more executable pages, as I mentioned earlier. So we're still kind of limited at this point. So what we're going to do is look at what else the GPU can access. And what you can see is that, of course, there's this entirely separate memory region that GPU can modify. So it can access most of the system region, and the system region contains a few things. It contains the home menu, as I mentioned, because that's an applet, contains the internet browser, and it contains actually a single system module, which is called NS, which we think stands for Nintendo Shell. We don't really know. So let's look at this. First, we've got NS code well beyond the GPU cutoff. We've got menu code, which is also well beyond GPU cutoff. But we've got the menus heap right here. Well, actually, there's separate heaps. These are well within the GPU's range, so that's good. NS, unfortunately, is still well beyond the cutoff, all of its data, all of its code. So we apparently can't get to that. So then the idea is just, well, okay, so actually, what's interesting here is that the cutoff is right before the end of the system region, which, as we just saw, has some interesting things, but also excludes all of base region, which also has very interesting things. So it seems likely that Nintendo knew about the capabilities of GPU DMA, like nefarious capabilities, but they didn't do anything about it. So it seems that they probably didn't realize what we could do with it, which is a lot. So yeah. Basically, we got menu heaps, so what we do is, since we have a heap, and this is all C++ code, we're just going to find an object inside the heap and overwrite it. So it's pretty simple. You just find an object that's going to be triggered through some kind of synchronization mechanism. In this case, it's going to be just return to menu. And we create some kind of fake vtable and get it to run our own stack pivot. And then we get ROP execution under home menu. Which is cool. We still don't have code execution on our home menu, but that's okay. So we can do a bunch of stuff with ROP. We can access a new new service, which is called NSS, which is very helpful because it can kill any arbitrary process as well as create new ones. Also gives us access to the SD card, which most applications actually don't have. And it lets us decrypt, dump any title on the system. So any game, even if you use this new cryptography that Nintendo introduced, we can actually dump that because for some reason well, home menu apparently needs access to that. And then we can also access and overwrite all of extra data used by any application, which is great. So we use this as a base for running Homebrew. Our Homebrew launcher is essentially just a service that runs in the background on our home menu process. It's written in ROP, which is kind of disgusting, but it works. The service handles running Homebrew, so the process is very simple. You just kill the current application, you spawn a new one, and then you take it over using the GPU DMA access, DMA. And then what we do is we send all of these new capabilities that we got through handles to the new process, and that gives us some higher privilege Homebrew. It also handles events such as home button, power button, all that good stuff. Which is nice because we can actually run code under any arbitrary application or game. So we can actually modify these games. We can run ROM hacks. So there's been a bunch of translations that can be run through this for games that haven't come out outside of Japan. So that's pretty nice. It's the same principle. You just launch the app, you take it over, you patch the code, and then you jump to it, essentially. All within the confines of userland, which is nice. So the other thing is we can actually access any game or application's data because we can run code under it. So these things include save game data for any game. So we can actually install more convenient secondary entry points, which do not rely on the browser, which can be patched at any moment, or on some old game. So some examples include Menu Hacks by Yellowzate, which exploits faulty theme handling code, which was introduced in firmware 9.0. Which is really nice because this way you can actually just run Homebrew right as home menu is opened, so right on boot time, which is great. Then you got other games. Of course, you got a Zelda game that's vulnerable. This time wasn't the horse's name, but pretty similar. And then you got other games. We got tons of entry points at this point, really literally drowning in them. So this is nice. But we forgot about Nintendo Shell, right? It's a very attractive target for a couple of reasons. For one thing, it has access to the AMU service, which can be used to downgrade any system title. It's not actually designed to downgrade titles. The thing is, it can both install and uninstall titles. So what happens is, if you uninstall a title and then install an older version of the title, you actually bypass the version check. So you can just do that to downgrade any system title and bring back old exploits if that's necessary, assuming you have access to the service. And of course, it's in a region that we can partially modify, so it's an interesting target. Unfortunately, we can't actually access this data right now, but maybe we can actually move it to somewhere that we can. The idea is, if you were to kill NS and then allocate something in its place, and then run NS again, you can move it below the cutoff. Thanks, but unfortunately, it's not that simple. That can't work. The reason being that we actually need NS to be running to launch NS again. So that kind of sucks. But, well, no, actually, we also can't run a second instance of NS at the same time, so we can't do that either. But interestingly, well, the 3DS has an interesting feature, which is called Safe Firm Mode. Basically, it's the second firmware, which is an old version of the regular one, and that creates a bunch of copies of system titles, most of them anyways. So that gives it a different ID. So the idea is, if it's got a different ID, we might be able to run it at the same time because, well, PM might fail to notice that. Of course it doesn't. It actually does notice that. So we can't run a safe mode version of a title at the same time as a regular version of a title. But for some reason, in the case of NS, well, you might not be able to see this very well, but so we've got NS, the regular title right here, and then we got safe mode NS right here, and for some reason they created a new 3DS version of safe mode version of NS, even though there is no safe mode, there is no new 3DS version of the original NS. So that creates a separate title ID which we can run at the same time as regular NS. So then the exploit becomes very simple. You keep NS running, just allocate enough data that it'll be below the cutoff, and then you just run new 3DS safe mode NS. And then it's within range of the GPU, and you can take it over and have access to everything. So this is nice. It's more of an oversight than a vulnerability, well, than the proper exploit, but whatever. So this gives us access to a bunch of system calls, mostly service handling system calls. So we can host our own service, which can be useful for other exploits that I won't get into, for impersonating other services to other system modules. And then we got access to all of these services, which is great. So we can downgrade system titles arbitrarily. And this runs in the background, which can always be helpful for Homebrew. The only problem is, at this point, it's still New3DS only because it relies on this New3DS title. But there are actually ways around that. And yeah, so this was just to show that we can actually get fairly high levels of privilege, even still just always staying in userland on the ARM11. And there are other similar attacks to that. If you're interested, you can look up RO hacks, which is a similar attack in the system module. So now Derek is going to talk to you about exploiting the ARM11 kernel. Derek?
So, hi everyone. First, I will give you some very short inside view of the kernel, and then I will explain how you can exploit the latest version of the ARM11 kernel. So, this is actually Nintendo's very first gaming console kernel. Like on any other older console, there was no kernel. All games were just running on bare metal. Like there was a kernel for the Wii, like a very small microkernel running on the security processor, but that wasn't written by Nintendo. And yeah, so it's the very first gaming console kernel. Also, that kernel is made to be thread safe, so it can run on multiple cores at the same time. And there are like 130 system calls available. So that's quite a lot in my opinion. But usually if you have gained execution in ARM11 userland, you only have access to like around 50 system calls. And there's a reason for that, but I'm going to explain that in a second. So internally, the kernel works with C++ objects. So here are some examples for system calls. So we have create semaphore, for example, that will just create a semaphore object in the kernel, and it will return a handle to the userland. And when you want to do any operations on it, on that semaphore, you have to pass that handle to the kernel, and it will look up this handle in a handle table to find the original C++ object. Also, there are two different kinds of memory allocators. So we have a memory allocator for the main memory, which is the FCRAM. And there's also a slab heap where all the C++ objects are stored in. And this slab heap is located in XCRAM, which is the ARM11 memory, where all the kernel code and data is in. Also, there's an IPC system. IPC is inter-process communication, and it basically allows you to talk to other processes, like like services, for example, the GSP service, or FS, or yeah. So let's look at the security. So the kernel is really small. There are only like 200 kilobytes of code, which is pure ARM code, and there are only like 1,000 functions. So they try to keep the code size very low, and that makes it harder to find bugs. Well, the code size is really small, and you don't have like really much to choose from what to exploit. Also, there are no symbols included in the kernel. Like when you run strings on it, it will just give you some names of C++ objects, but there are no function names or something like that. As we have seen earlier, it's physically isolated in its own memory, which turned out, of course, to be a good idea. Otherwise, it would have been overridable by the GPU eventually. And all objects have a reference counting. So that's similar to the C++ shared pointer, where every object has a small field, like a counter field, and every time the kernel wants to use an object, this counter gets increased. And every time like when the reference is no longer needed, it will decrease that counter, and when that counter reaches 0, it will automatically delete that object from the slab heap. So they are basically trying to prevent use after freeze. Also, I'm not sure if that's a security measurement, but there are more than 100 panic calls in the kernel, and like that's every 10th function per average. And they have this syscall access restriction. So you, as I said, you only have access to like 50 system calls, and all the interesting ones are disabled. For example, you can't map executable pages. Yeah, on the other hand, there's no ASLR, but at least they are trying to change the memory mapping every time they are doing a larger kernel update. Also, there's no stack protection, and the user land is always mapped. So once you've got control over the program counter, you can just jump to user land pages that are marked as executable. So you don't have to do ROP in the kernel, which is pretty nice. Yeah, but they tried to have an execution prevention in the kernel. That is, they are marking executable kernel pages. That is the code. They are marking them as executable in the page table. So let's take a look. So the highlighted parts in orange are the kernel code sections. And as you can see, like when looking at the first highlighted line, it says virtual address FF00 and so on is mapped to the physical address 1FF8000000, and it is marked as executable, and you only have access to it in kernel mode, of course, and only read access, right? So this is correct. But when you look at the second line of that page table dump, you will notice that there is another section which covers the entire XERAM, and it's mapped as read-write. So it doesn't really make sense. Yeah, so basically it's completely useless. We have read-write access to it. So to summarize everything, there's actually no exploitation protection. Once we found an exploitable bug, it's pretty likely that we will gain code execution in kernel mode. Yeah, so let's find that bug. And I started at looking at the SVC table. So this is kind of the interface between kernel land and user land. And this shows all system calls that are available in the kernel. So you have like normal system calls. For memory management, you can map read and writable pages. You can mirror pages and do other memory management stuff. And there's also some configuration for threads, like you can choose which core should be used for executing the thread and all that stuff. You have a really large range of synchronization objects, like the kernel mutex and all that stuff. And of course, you have IPC requesting, so you can send messages to services. And there's a more advanced section, like this is used by services mostly, because they have to respond to your IPC requests. And there's also kernel DMA, cache control, some things. And they have a set of debug system calls. Yeah, it's just basic debugging. You can set breakpoints, read and write, process memory, but yeah, you don't have access to them. Like on retail, it's not actually used. And so one last section is the privileged section. And here are all the very interesting system calls that allows you to create processes and execute, map executable memory and all that stuff. So unfortunately, we can't use the advanced debug and privileged system calls. I mean, that would require exploiting some servers. And yeah, that's just more work for us. So this leaves us with the normal system calls. But yeah, IPC sounds really interesting, but unfortunately it's full of panics. Yeah. Also, there's not much to attack at synchronization, object calls, system calls. So we only have like this more interesting system call for local memory management. And in theory, there's a lot that you can mess up, right? There's a lot that can possibly go wrong. And also we have unchecked DMA access, like through the GPU. So maybe we can do something useful with that. Okay, so let's have a look at the memory allocator. There are two types of memory allocators. First is the regular one. It's just for mapping normal heap, like for malloc in C, for example. And you have the linear memory allocator that is used for GPU textures, like when memory has to be continuous, physically continuous, you use the linear memory allocator. And there's the FCRM memory layout that we saw earlier. You have these three regions, and every region has its own set of free pages. So how are they keeping track of them? So you have a region descriptor, which tells us the dimensions, like where does it start, the region, and its size. And you get also a pointer to the first free piece of memory in that region. And each free piece of memory, which we call a memchunk, has a memchunk header right at the beginning. And it basically tells the kernel how large that memchunk is. And it's also linked in a doubly linked list. So you have the next and previous pointer pointing to the next and previous memchunk headers. It kind of looks like that. So you have the red parts, which are the free memchunks, and the green parts are memory that is already allocated. So allocation is pretty straightforward. It's not really complicated. So the first thing that the allocator function does, it loads the next free pointer from the region descriptor. And for regular memory, it just goes through the list, following the pointers. And it sums up their size until the requested size is reached. For linear memory, it would just look for a suitable memory chunk to make sure that that memory is really continuous. So when it found enough memory, it sets the next pointer of that very last memchunk to 0. It will then update the list and also the next free pointer for the region descriptor. And finally, it will return a pointer to the first memchunk. So let's look at this from a security perspective. And there's a problem. They basically have kernel structures inside the FCRAM. And that is a problem because we have DMA access to it through the GPU. And there was an attack by Yellows8 that is called memchunk hacks. And what he did is basically he overrode memchunk headers with a GPU DMA flaw. And then he gained an arbitrary kernel write when it's deallocating memory. So because the next and previous pointers have been modified. So unfortunately, this was fixed by Nintendo in system update 9.3 last year, like 1 year ago. And the new kernel will now verify every memchunk header during allocation, like its size and also next and previous pointers. So yeah, in theory, everything has been fixed, and invalid pointers or invalid sizes will just result in a kernel panic. Yeah, so yeah, in theory. So when you look at the system call for control memory, yeah, we have access to it. It's one of the normal system calls. It does basic stuff. You can map in free read-write pages, but not executable, of course. And it takes an address and size as argument, and also a operation code, which tells the kernel what to do to map or free pages, whatever. And so first, it does some basic checks on the address, and eventually it will call a very large function. And I just call that function kernel control memory. So what kernel control memory it does, it calls the allocator function, and it will just return a memchunk header pointer, as we have seen earlier. And then it goes through all of the allocated memchunks, and it's mapping them to user space. And it's also updating some block information for a kernel process object. So there's a problem. There's obviously a race condition. Like, we can overwrite memchunk headers after they have been allocated. So we could try using the GPU, but it's really slow actually, because we would have to ask the GSP service to read memory, and yeah, we have to go to this very large IPC kernel code, and that would be probably too slow. Allocation is really fast. So let's dig a little bit deeper. Yeah, I tried to reconstruct the source code in C. So this is the first step. It tries to allocate memory. For this example, it will just allocate regular memory. And so when it found a memchunk, which means that that enough memory is available, it will then execute this really interesting do-while loop. So yeah, I know it's a lot of code. I'm not sure whether I can actually read it. So let's go quickly through this code. There are the pages, read from the memchunk header. It gets converted to a physical address, and that physical address gets mapped to userland by memmap function. And then it will go to the next memchunk here, and it will also update the userland virtual address, and then it will clear that memory. So what's wrong here? So the problem is they are mapping the memory chunk into userland, and after it has been mapped, they are accessing it again. And what they access is the next pointer. So we can just override it. Like when we have 2 threads running, we can, from another CPU core, try to override that pointer. So our goal would be to map kernel pages to user space, but there are some problems. It requires really, really perfect timing. There's only a very small time frame to do the override. And also we need a memchunk header structure at the next pointer address. So yeah, to do this. So to make sure we get a perfect timing, I came up with a kernel address arbiter oracle, and it is actually used for thread synchronization. We don't care about it, but it tries to read from address and returns an error when address is not accessible by the userland. So we can use that system call to make sure that the memory has been mapped to userland. And once it has been mapped, we are trying to override it. So one last problem, we have to inject a memory chunk header in kernel. So I did this by using this lab heap. We can just create some kernel objects and set their memory variables to create a faked memchunk header. So this is this lab heap. We've got C++ objects, vtable pointer, and some attributes. So yeah, this lab heap is basically just a really large area of C++ objects. And what I did was I changed the attributes and used them as memchunk header. And I am redirecting the next pointer to that object, and it will map multiple C++ objects to userland. And that's really nice because we have vtable pointers, so we can just override them. And that means that we gain code execution. So as a summary, we set up some kernel objects, change their attributes, request memory from the kernel. Once it becomes available, we patch the next pointer, override that map slab heap pages, and then we call a system call which closes the handle for the kernel objects that we created in step 1. So it will eventually call some vtable function, and it will just jump to our modified vtable function, and we got ARM11 level 0 code execution. So now Pluto will tell us what nice things you can do once you've gained ARM11 code execution.
Hey guys. Okay, so the ARM9. Yeah, let's go. Okay, so the ARM9 is actually also used for executing old DS games. So what they do is they actually, you could say, reuse the ARM9, which is their backwards compatibility processor. They use it for as a security processor when executing 3DS code. And like Svea said, it's running a stripped-down version of the ARM11 kernel. It basically only does threading, synchronization, things like that. There's no MMU. There's an MPU, 8 regions you can configure. You could do no execute within those regions, etc. But like the granularity is not very nice. So, and they only have 8. So they basically ran out of space, and data and stack is executable as long as you can jump to it. And text is writable, so that's bad. Basically, whenever you have whenever you can write code into arbitrary memory, you can just overwrite code. And yeah, these features, you don't want them on a security processor. Okay, so let's go. So it turns out that there have been a lot of exploits over the years, and most of them are fixed, and most of them use the normal command interface. But in this case, we're taking a different approach. So on the 3DS, the memory mapped I/O is split up into 3 regions. There's the ARM9 only I/O. It does crypto. It does it has DMA engine, things like that. And then there's the shared I/O region. And then finally, there's the ARM11 I/O region, which contains the GPU, video decoder, So thanks to Derek and Smea, we have full ARM11 control. We execute kernel mode. So the question is, can we use the shared I/O region somehow to own the ARM9? Okay. So it turns out the interface for reading old DS cartridges is actually in the shared I/O region. We're not sure why this is, but they have it there for some reason. And it's only the ARM9 which is actually using this region, but ARM11 still has access to it. So when you insert a cartridge, it starts by reading the banner. And it does this by writing this magic value to control register. And basically, it just asks for 200 bytes, 200 hex bytes. So, and then there's this loop. And this pseudocode is on the right side. You can see it basically waits for some bit to clear, to set. And then they read 4 bytes. And then they wait for another bit. And there's no range check on the buffer. But it's always 200 bytes, so it should be fine. Well, what if we overwrite the control register from ARM11, asking for hex 400 bytes, 4,000 bytes? Boom. Okay, so we have a nice buffer overrun. It's in the BSS segment, but yeah, it's still nice. Can we control the data? So the data actually comes from the cartridge. And yeah, we need to make our own DS cartridge. So there's this old device called a PassMe. It's for the original DS, where you basically plug an old DS cartridge in, and it basically modifies the header as it's read. So these are available online for $5. And then you add an FPGA. So, I implemented this, and it works, but it's very gimmicky, and yeah, I don't recommend it, and yeah. And here's my soldering. It's not very nice. Okay, so this gives us ARM9 code execution, and this works on latest firmware, but we want something better. So let's look at the chain of trust. So the chain of trust idea is, of course, you verify all the code that is running, but basically verifying everything at load time. So the 3DS has the simplest chain of trust you can have. There's the boot ROM at the start, and then it loads a firmware binary from NAND, and it jumps to it. And on the new 3DS, they were a bit clever. They added an extra crypto layer on the ARM9 portion, but it's actually part of the firmware binary. And we call this ARM9 loader. So the theory that Nintendo had was, yeah, let's add another layer of crypto. So we change the keys, we introduce new keys, and they can't break it. So, and they don't have anywhere to put those keys, so they place them in NAND. But they're encrypted with a per console key that's based on a hash of the OTP that's unique for each console. And then OTP access is disabled early in the boot, so later on you can't dump the OTP and you can't figure out the keys. So this looks safe in theory. So here's their implementation. So they calculate some hash of the OTP, they read the key sector from NAND, and they decrypt the key, and they put it in a key slot. It's basically isolated memory area. And then they generate a bunch of subkeys, and they verify that the key they loaded from NAND is the correct one. So even if we were to switch the key, they would detect that and just panic. And then they decrypt the ARM9 binary, and they jump to the entry point. But they forgot to clear the hex 11 key. So we can just get code execution later on, and we can just regenerate all of those keys. So this implementation is useless. Okay. And they fixed this because they have more than one key hidden in the NAND. So they took their next key. It's basically the same idea. You calculate the same hash, you read the key sector from NAND, you generate all the previous keys for compatibility, and then you decrypt a new key we call it key number 2, and then you decrypt the ARM9 binary using the second key, and you clear the key slot, and you jump to entry point. But they forgot to verify the second key. This is epic fail. Okay, so let's exploit this. So ARM9 loader hacks. We can change the second key. ARM9 loader will just decrypt the binary to garbage and jump to it. Okay, so if you look at the encoding of a ARM branch instruction, the probability is pretty high that it will just be a branch instruction. Just any random data will eventually, like if you try enough keys, it will eventually become a branch instruction to some memory. So if we try a lot of keys, basically, eventually we'll find some garbage that is useful. So this is the NAND of the flash memory of an unmodified 3DS. a new 3DS. So there's a small key section marked in teal, like blue, and it contains those keys that we're talking about. And then there are two firmware partitions. One is used for backup in case one gets corrupted, so it doesn't brick the device, whatever. So we install our custom key, and we install the largest firm binary we have in the firm 0 partition, and we keep the one with the vulnerability in the firm 1 partition. And then we put our code payload on top of the firmware 0 binary. So, and then we reboot. And so what will happen? The boot ROM is executed. It will load the first firmware partition. And it has our code in the end, but it doesn't know about it. And then it decrypts it. And you see, it looks okay. There's the ARM9 loader stub in the front, and then comes the encrypted binary. And then finally, there's our payload. But boot ROM checks the hash, right? And it fails. So it thinks the partition got corrupted. So it will load the smaller one on top. And you see, we have our payload in memory at boot. And then it decrypts firmware 1, which is smaller. And it still has ARM9 loader and another encrypted ARM9 binary. And then it jumps to ARM9 loader because the hash checks out. And then the ARM9 loader will decrypt our corrupted key from NAND. And it will decrypt this one to garbage. And it will jump to it. And hopefully, it jumps to our code. So this gives us ARM9 code execution from cold boot early, very early. So it turns out we can actually use this to get some keys that are later not available because they clear those. They use a certain memory area for seeding an encryption engine to generate keys, and those keys are later, the memory is later cleared, so you can't regenerate the keys. But with this, we can actually get those two keys. They're called firmware 6 safe key and firmware 7 NCCH key. So that's a bonus. Okay. So we talked a bit about the AES engine. It's used everywhere for the crypto, and it's used for everything, basically. It supports all the usual block cipher modes. It has two security features. It has write-only keys, which is really useful. Like, you write a key, and then you can never, ever read it back. This means that they can fill in the keys by the boot ROM, and basically this will, and we can't dump them later. So they can keep the keys secret. Even if we hack the ARM9, even if we get code execution, we'll never get the keys. And then there's the key scrambler, which is that the key is actually, it's an optional thing, where the actual key is hidden, calculated by a hardware function that is never, that we don't know about. So the key is actually never exposed to the CPU, the actual key. So we just feed it two values, two keys, and then it generates a new key based on that. And we don't know what that key is. So this creates a situation similar to the isolated SPUs on the PS3, where you can ask it to decrypt stuff, but you don't get the keys. And if you don't get the keys, then, yeah, we want the keys. But, yeah, we want to decrypt things on our PC because we're lazy. So there are two keys, key X, key Y, we call them. They're 128 bits, and the normal key is derived as a function of those two. And that function is unknown. It's implemented in hardware, in silicon. And the key here is, yeah, so even if we know X and Y, we can't figure out the normal key, and we can't decrypt things without asking the 3DS first. But we can poke this hardware engine. So And the first thing you notice when you do this is that if you set the nth bit of the x key and the n+2 bit in the y key, you get the same result. And in general, you find that the function that we're looking for is actually just a function of one variable, where it's the XOR between the x rotated by 2. So this is rotation, not shift, and XORed with y. But we still don't know g, but we want to know g. So let's see. But yeah, so step back a little bit. So the key scrambler is used for me QR codes. It's used for everything, right? So it's used for a network protocol called UDS, and it's used for download play, which is when you download games over Wi-Fi, temporary games. But the Wii U also supports all of these, but it doesn't have the key scrambler in hardware. So the Wii U must be using normal keys. Okay, so we make a table of the shared keys, and basically these are the 3 keys that are shared with the Wii U, and who is where the key X and key Y on the on the 3DS where they are set, and 2 of them have key Y set by firmware. So we can't read the keys set by the boot ROM because it's locked away and we don't have it. But can we still figure out G? Let's see. So I'll give shout out to Shuffle2 and to Failoverflow, who hacked the Wii U. And they helped us, or Shuffle helped us extract the Wii U keys. So thank you. And so now we have key Y, and we know the normal key from the Wii U. However, key X is still unknown. And if G of t is bad, then a small change in the key Y will only lead to a small change in the normal key. And yeah, it's bad. Okay, so let's look at the data. So when we flip 1 bit in the key Y, we can brute force all keys similar to the normal key, which is just within a couple of bit flips. And we find that it always results in a normal key with bits flipped at position either 87 or 88, sometimes 89, but never 86. So this reminds me of like an adder where you had a carry bit being propagated to upper bits, but never to lower ones. So let's guess that this is an adder, and let's try. It's an adder with a rotation. So we guess that G of t is t plus c, some constant c, we don't know it, and rotated to the left by 87. And then we plug it into our original formula. And we don't know key X, remember, because it's set by boot ROM, and we don't have it. And we don't know the constant C because it's in silicon. So it's in hardware. But if we look at our formula and we consider the inequality, where we basically rotate right by 87, we're basically undoing the outer rotation. And then we plug in our formula, our guess, and then we get this. And then we subtract C from both sides. We end up with this. And this is basically, we're XORing 2 different keys with the same X value, rotated to the left by 2. And well, if you stare for this a bit, you'll see that if Y0 and Y1, which are 2 different key Ys, are equal except for at 1 position, 1 bit position, then the XOR is smallest for the one which has the same bit, which shares the same bit value at the position that the 2 Ys are differing at. So it's actually pretty simple, but it sounds difficult. But like XOR is 0 if they're the same input and 1 if they're different. So if they're same, it's 0 and it's smaller. So we actually look bit by bit on this, and we repeat this 128 times. and we recover all 128 bits of the key X. And when we have the key X, we can calculate the silicon constant C. So the end result is the key scrambler is figured out. And we have also the secret bootrom key X for a couple of key slots as a bonus. Yeah. Okay, and also, so I didn't include the constants in the slides because I want this to be an exercise for the listener. So they actually, when the new 3DS was released, they rushed it, we think, because they left some interesting commands in the PSPS service. And it included an early version of the NFC crypto used for the Amiibo figurines. And this implementation, the first one, uses a normal key. And when the newer one changed it to a key Y. So they accidentally gave us one of these pairs in the firmware images. We don't need to use the Wii U at all. So anyone who can decrypt 3DS firmware binaries can perform this this attack to get the constant. So anyone out there, yeah, good luck. Okay, and now back to Smea for summary.
All right, so just going to conclude really quickly. So some takeaways of what we talked about today. First thing is, it's all pretty obvious lessons, but bear with me. Giving access to physical memory to any application through the GPU or whatever is dangerous. You should always be careful about that. Even if you think you've protected stuff, there's probably going to be stuff that you forgot. So just either don't do it or do it right. Other thing is, shared I/O is dangerous. If you don't know what can actually control the I/O, then, well, again, you should be very careful. Also, only checking your data before decryption is dangerous, and, well, both that and not checking the key when you know that it could possibly be modified by an attacker is a bad idea. And finally, secrets hidden hardware are great unless you give them away, so don't do that. Beyond that, we just wanted to talk about the state of homebrew really quickly. You might recall during the Wii U talk around here 2 years ago, that Velverflow said that they didn't think necessarily there was much of a future for console homebrew. And there's definitely an argument for that with the rise of, well, phones mostly. Anyone can make an app, can make a game for any number of devices and sell it to, well, millions of people. But you know what? We disagree. It's been a year since we started releasing 3DS Homebrew. And, okay, so this is supposed to be moving, but let's imagine it's moving. Well, there's been a bunch of 3DS Homebrew. It's been awesome. We've been working on this really hard. A lot of people have been joining us. It's a great community effort. And basically, what I want to say is, well, we want more developers. So if you would like to join us, there is a very, well, it's not very mature, but it's maturing, our SDK. And you know what? Reverse engineering hardware is fun when we don't have any documentation. Reverse engineering software is fun. We can always use more reverse engineers and just people who want to make cool shit. So, yeah. Oh, right. Just one more thing. Lately there has been a wave of patches by Nintendo of known exploits, which has been really annoying. So for our browser hacks, well, Yellowzade's browser hacks, menu hacks, stuff like that. Yellowzade's been working pretty hard. He actually brought back browser hacks. It should have been released about 10 minutes ago. So. Not only that, but we also had iron hacks for an eShop game, a free eShop game, so you could just download it. That was patched. The thing is, there's actually a way to download the old version from the eShop application with some patches. So we're also releasing that right now. So basically, if you can get Homebrew and get onto the eShop with a modified patch, that should also be released in about, well, whenever this is done. So get it as soon as possible. This is a free game. It'll get you Homebrew forever, so just do that. And also, Yellowzay just released a new version of Menu Hacks, which works on latest firmware version. This was also patched like a couple weeks or months ago. So this is all out right now. If you have a 3DS, get it. If you have friends who have 3DSs, well, tell them to get it, because it might not last super long. Yeah, so we would like to thank Yellowzay, who unfortunately cannot be here tonight, but has been super helpful, has been doing a ton of work on the 3DS, and like honestly, a ton of this could not have been done without him. And thanks to everyone on the 3DS Dev Homebrew channel, everyone who's attending tonight, thanks for this. And yeah, if you have any questions, I don't think we have a lot of time, but we'll accommodate. Thanks.
Thank you for your patience. If you got questions, please come up front to these guys because we have no more time for structured Q&A. Thank you.